Today we're going to begin Module 20, which is about dilations and similarity. So in our previous module, Module 19, the transformations that we learned about, they changed the location or the direction that your figure was facing, but the size and the shape remained the same each time. The reason why dilations have their own module is because they are a little bit different. What we're going to notice is one of those things changes versus the previous transformations that we've been doing. Okay, so for this lesson, we're going to actually take a look at our explore activities. So to begin, we're going to read this together. Explore activity number 1. The missions that placed 12 astronauts on the moon were controlled at the Johnson Space Center in Houston. The toy models at the right are scaled-down replicas of the Saturn V rocket that powered the moon flights. Each replica is a transformation called a dilation. Unlike the other transformations you have studied, translations, rotations, and reflections, dilations change the size, but not the shape of a figure. Okay, so what you can see here are these replicas of the rocket, okay? So what you notice is the shape stays the same, it's just getting a little bit smaller. This is called a dilation. Every dilation has a fixed point called the center of dilation, and that's located where the lines connecting the corresponding parts of the figures intersect. So what does that mean? Point C is the center of dilation. So the corresponding parts of these two figures, for example, R and the image of R, which is here, R prime, they're corresponding parts. So if we drew a line straight from one to the other, and I did that for all of the other corresponding points, they would all meet at C. Same thing for our rockets here, right? Look at the tippity top and the bottom, they meet at that center of dilation. Okay, so I cut out the measurements for these because I can't be sure that you guys have rulers and all of that stuff at home. But if you measured each of these segments here, for example, CR and CR prime, and you noticed, and you measured CS and CS prime, CT and CT prime, and you wrote those in the table. If you find the ratios of those from the original to the image, you'll see that the ratio is the same each time. Okay, so we're going to look at that in depth, but the idea of the dilations is that even though the size has changed, the ratio remains the same. That's what keeps the figures the same shape. Okay, so let's actually do the reflect. Two figures that have the same shape but different sizes are called similar. R triangles RST and R prime S prime T prime similar. Why or why not? Well, if we take a look at these, the corresponding sides of them are proportional, which you don't know because you didn't measure it, but looking at the table that's filled out, if it's already measured, you can see that. So like I said, we're going to talk about that and you're going to see it for yourself. But just for the Explorer, I'm just going to tell you the sides are proportional to one another. So if I measure this side, let's say, I'll tell you that it's 2 centimeters when you measure it. And this one is 1 centimeter, okay? And ST is 1 centimeter as well. And S prime T prime is 2 centimeters. And then when you measure RT is 1.4 centimeters, and it is equal to 2.8 centimeters once it's been dilated. So what you want to do is look at the results versus the original. So RS was 2 and the original RS was 1. So the ratio is 2 to 1, which is a 2 equal to 2. S prime, T prime is 2, and ST was 1, so that ratio is equal to 2 as well. And then finally, R prime, T prime is 2.8, and the original was 1.4, and that is also equal to 2. So this tells me that they are proportional because the ratios are all equal, right? So because they have the same size, the same shape but different sizes, they would be similar. So yes, they are still similar. Yes, because their corresponding sides are proportional. Let's say corresponding sides are proportional. Okay. The orientation, that word we are using to refer to the direction in which the shape is facing. So how would you describe the orientation? Do they have the same orientation or is it different? Well, the shapes seem to be still facing the same way. The only thing that's changed is the size. So their orientation stays the same. Okay? Stays the same. So let's take this from the Explorer activity here to the second Explorer activity, which brings us to the coordinate plane where things are a little bit more structured. Okay, and this one's gonna make a little more sense to you, I promise. Okay, so in this activity, we're gonna explore how the coordinates of a figure on a coordinate plane are affected by a dilation. So we're gonna fill out this table. Okay, what I would like for you to do is I would like you to try to fill this out on your own. I'm gonna keep going with the lesson, but you can pause it if you'd like. We're gonna write the X and Y coordinates of all of the points for the image, and then all of the points of the original. Remember that the image has the little dash above, which means prime. And then after you've done that, we're gonna do the ratio of the X coordinates and the ratio of the Y coordinates. So for our image, look at your graph and you can see the image is the one with the prime. So A is equal to 1, comma, what is this, 2.5? This is in between, so that's 2.5. So it's 1, -1, sorry, and 2.5. B is 2, comma 1, 2, comma 1, okay? C is 2, -2, okay? And D is -2, -2. Okay, so those are the points for the image. Now we're going to look at the original, or the pre-image. We're going to write those coordinates. So A is here, so that's 2, 5. 2, comma 5. B is over here, 1, 2, 3, 4, up 2, so that's 4, comma 2. C is down here, so that's 4, -4. And D is over here, which is -4, -4. Okay, now that we've filled out all of those coordinates, we're gonna now look at the ratio of the X coordinates. To do that, I take the image and I divide it by the original. So I'm gonna just use a different color pen to try to help out here. We're doing the X coordinates. The image is -1 and the original is 2. So this should hopefully be kind of ringing a bell when we did proportional relationships in linear equations, where we looked at the y, we did y divided by x, and every time if we saw it was the same, then it showed it was in proportion. This is going to be the same thing. We're going to divide the image by the original. Okay? This should be -2. So sorry about that. Okay? So this is -1 divided by -2, which is 1/2. Or 0.5, okay? Let's just do all the X coordinates first. Next, we're gonna look at the second point, the image divided by the pre-image, so 2 divided by 4, which is equal to 1/2. Okay? Next, for C, 2 divided by 4, again. Okay, and that's also equal to 1/2. And then finally, -2 divided by -4 is also equal to 1/2. So like we kind of were probably predicting, you can see that all of the ratios of the x coordinates are equal. They're all equal to 1/2. So now let's take it to the y coordinates, and we're going to find the y coordinate ratios. Same exact way. This time we have 2.5 divided by 5. Okay, so that's 2.5 over 5. And hopefully we know that 2.5 is half of 5, so that's equal to 1/2. Then we have 1 divided by 2. And again, that's just equivalent to 1/2. I'm just going to write it again so they're all in line. -2 divided by -4. -2 divided by -4 is also equal to 1/2. And last but not least, -2 divided by -4 is again equal to 1/2. So as you can see, the ratio remains the same throughout. So this is how we keep the shape exactly the same when we do a dilation. If we take each point and we multiply it by the same number, in this case 1/2, we will be able to keep our shape exactly the same, and that's what a dilation is all about. So what you notice is that if you took point A, which had the coordinates -1 and 2.5, if we multiplied that by 1/2, we get the result. I'm sorry, this was the original. -2 times 5, and we multiply it by 1/2, we get -1 and 2.5, which is here. For point B, it was 4, 2. We multiply that by 1/2, and we get 2, 1. And this goes for each of the points, okay? So it says write a conjecture about the ratios of the coordinates of a dilation, okay? And in this case, the ratios are all equal to 1/2. You can also say they are all in proportion, or all proportional, whatever you'd like. Okay, and this is what makes a dilation a dilation. So just really quickly, this last reflect question. In the first activity, the triangle image was larger than the original, right? So we started off with this one, and we ended up with this larger one, okay? However, in this example, how is it different? We're starting off with the larger one, and we're ending up with a smaller one, okay? So how is it different? The image of ABCD was smaller instead of getting larger, okay? So those two activities were explore activities, okay? So now we're going to start talking about this in a structured sense. So in those two activities, what you saw was that a dilation can either produce a figure that's larger or a figure that's smaller. If your original image becomes larger, we call it an enlargement. If the original figure becomes smaller, we call it a reduction. Then there is something called a scale factor. And the scale factor is the number that you are multiplying by in order to get the new figure. So in our previous example, we saw each time we were multiplying the coordinates by 1/2 to get that reduction. So our scale factor would have been 1/2. So to find the scale factor, what you just have to do is find the ratio of the image to the original. So before we start, I'm just going to write this down because it's not written. To find the scale factor, you do the ratio of the length of the image to the length of the original. Okay, and what that ends up looking like is always image over original, or you can call it the pre-image as well. Okay? Okay, so let's take a look at an example. An art supply store sells several sizes of drawing triangles. All are dilations of a single basic triangle. The basic triangle and one of its dilations are shown on the grid. Find the scale factor of the dilation. So in order to do this, what you need to do is you need to look at the coordinates of the image compared to the original, just like I showed you with the scale factor just before. So what we're going to do is we're going to write the coordinates and we're going to find the length of each side so that we can figure out what this scale factor is going to be. So if I look at A prime, it is equal to 3, 8. Okay. B prime is 9, 4. And C prime is 3, 4. Okay. And the originals were A, 1, 3, B, 4, 1, and C, 1, 1. Okay, so what we're going to do is we're going to look at the length of each of these triangles. AC is 2, okay? If you just count 1, 2. The corresponding side here in the image would be 1, 2, 3, 4. Okay. CB, 1, 2, 3. And the corresponding side in the image would be 1, 2, 3, 4, 5, 6. Okay. Sure. And as far as this diagonal goes, we can't really measure them just counting because it's diagonally on the triangle. Okay, so what we're going to do is we're going to, now that we find the lengths of these sides, we're going to find the ratios of the corresponding sides using what I said before, which I said was image over original. So the image is the one with the prime, remember? Okay, so the image, we're going to do AC, A prime, C prime over AC. So it's 4 to 2, 4 divided by 2. That will give me 2. And now we're going to do the second side length that we're given. C prime, B prime over CB, which is 6 over 3, which is also 2. So we can see that our scale factor is 2. Okay, and that's it. Is the dilation an enlargement or reduction, and how can you tell? So when you start at your original or your pre-image, it's smaller and it becomes larger. So this is an enlargement. It's an enlargement because triangle A prime, B prime, C prime is larger than the original triangle, ABC. That's it. Okay. So I included the your turn, but I also added in 2 questions so that you guys can practice a little bit more before you start the homework. So we'll do the your turn together, and then you guys will try 17 and 18. We're going to find the scale factor of this dilation. So again, instead of looking at just the coordinates, I wrote them all out before, but it was kind of unnecessary. We're going to just count the side lengths, okay? And then we're going to do the same thing we did before. So we're going from the image to the back to the original when we do the ratio. So try to remember that. It's not always the largest to the smallest. So in this case, your image is smaller than the original. So this would be a reduction. Okay? So let's count this side first. D prime, G prime. And we're going to compare that to the original DG. So D prime, G prime is only 2, but the original DG was 1, 2, 3, 4. So this is equivalent to 1/2. Now let's see if all the others are the same. Let's do D prime, E prime. So we're going to do D prime, E prime, and compare that to the original DE. So D prime, E prime is 1, 2, 3. And we're going to look at the ratio to the original. 1, 2, 3, 4, 5, 6. 3 to 6 is equal to 1/2. So far we're good. Let's now do E prime, F prime, and E, F. E prime, F prime to E, F. So this is 2. And the original was 1, 2, 3, 4. Which is equivalent to 1/2. And now finally, G prime, F prime, and G, F. G prime, F prime to G, F. This is 3 to 6. And again, that's 1/2. So each time, the ratio is equal to 1/2. So the scale factor is 1/2. And that's your answer. Just the most important part here is to remember that when you do your ratio, you're doing the image divided by the original. So why don't you guys pause this, try 17 and 18, and then unpause to compare your answers. Okay guys, so when you look at 17, what you should notice is that the original is smaller. So because the image is getting larger, this is going to be an enlargement. When you compare each of the ratios from the image to the original, you can see that they're square, so they're all going to be the same. And each time, the ratio is 6 to 2, which is 3. So your scale factor for number 17 is 3. For number 18, there's only one straight side that you can use to find your scale factor, but that's okay. You look from the original to the image and you can see that it's gotten smaller. So this one is a reduction. And when you find the ratio, you see that it is a 2 to 4 ratio, which means that your scale factor is 1/2. If you want to start thinking about it this way, in the next lesson, what we're going to discuss is all of the dilations and algebraic representations. See if you can figure out what the pattern is. Every time it's an enlargement, the scale factor looks a certain way. Every time it's a reduction, the scale factor looks a certain way. Okay? So you can start thinking about that while you do your homework. And today is, what lesson is this? Is this Wednesday? This is Wednesday. Okay, so Wednesday, you guys have office hours tomorrow. So if you have any questions on the homework, make sure you bring them to the office hours and you can ask. Okay, have fun.